Everybody, welcome back. And now we're happy to have Suvrat Raju from ICTS, who is going to tell us about holographic null infinity and the information paradox in flat space. Suvrat.
Okay, thank you very much, Anastasia. Thank you very much also to the organizers for organizing this wonderful conference. I'm sad that I wasn't able to visit South Africa for the conference, but I hope I get a chance to visit soon. Before I start my talk, let me just acknowledge my collaborators. So I'm going to speak about work that's done in collaboration with Pushkal, Chandramouli, Bidisha and Siddharth at ICTS, Olga and Kyriakos at ICTP, and Alok at the Chennai Mathematical Institute. I'm largely going to talk about this paper we wrote a few months ago with Alok, Siddharth, and Pushkal, but I'll also describe some work in progress that should be out soon with Chandramouli, Olga, and Kyriakos. So before I start my talk, let me just try and explain what the main idea that I'd like to convey is. So we've understood AdS-CFT now for many years. And when we say that quantum gravity in anti-de Sitter space stores information holographically, we are referring to a very special property. And that very special property is as follows. If you consider some Cauchy slice that runs through AdS, like this slice on the right-hand side, this slice might have some excitations or some features that live very close to the middle of AdS. But the statement that the theory is holographic is a statement that you can immediately read off the form of this bulk excitation from this little red region near the boundary without waiting for the signal to emerge at late times. You could wait for the signal to emerge at late times if you so wished, but holography tells you that you can also read off the signal just at the same time. So the main announcement that I would like to make in this talk is that we have been able to establish a similar result for gravitational theories in four-dimensional asymptotically flat spacetimes. And the result is as follows. If you consider a theory with massless particles, one might have thought naively that the information about the massless particle is spread out all over future null infinity, and that is indeed the case in a local quantum field theory. What I'll try and describe is that in a theory of gravity, this information can be obtained just from the past boundary of future null infinity, which is a region marked in red on top. There is an analogous statement for past null infinity, in which case the information can be obtained from its future boundary. But to avoid duplication, I'll only make statements for future null infinity in this talk, and there's always an analogous statement for past null infinity. So that's the main result that I would like to convey. Now, there is some difference with the situation in anti-de Sitter space in that null infinity, even in a gravitational theory, I'd like to explain, stores information more intricately than the boundary of anti-de Sitter space. So one of the points I would like to describe is that unlike anti-de Sitter space, we tend to lose information as you move along the boundary. And what that means is that if you look at the information that's available on this magenta cut or this purple cut, it's a subset of the information that's available on the red cut. And the general rule is that the information on later cuts is a subset of the information on earlier cuts. Okay, now one of the points I'd like to emphasize is that even though I'll talk about operator algebras and some technical aspects in my talk, this is really not an abstract result. The result I'm describing leads to a very concrete physical protocol for observers near the boundary, for observers who live in this region near the past boundary of future null infinity, to identify the bulk state. So at the end of the previous talk, there was some discussion about what if you had a shock wave that was blue or green and how you would be able to identify that from far away, and I'll try and describe how one could do that in a theory of gravity. I'd also like to explain that this has direct implications for black hole information. In particular, there's been an idea which was also discussed in the previous talk, which was that it may happen often in a theory of gravity that degrees of freedom that look like superficially they're localized on different parts of a nice slice may need to be identified with each other. So this is an idea that was articulated clearly at the time of the debates on the firewall paradox in papers by Kyriakos and me, by Rick and Herman, by Yasunori, and subsequently also by Juan and Lenny, and going on to the more recent discussions on the island proposal. And what I'd like to explain is that this notion I'm describing of how information is stored in null infinity makes it precise and also suggests a physical origin to this idea. And the way it does that is that if you think of a black hole spacetime and think of this nice slice, you might have thought that the information that lives in these green dots is the information that emerges on later parts of null infinity, which is this green segment. But if it is true, as I claimed, that the information on the green segment is also available on this red segment, that's a precise version of the statement that the information in the green dots or degrees of freedom in the green dots need to be identified with some complicated set of degrees of freedom in the red dots. The perspective I'll describe will be a direct Lorentzian perspective, so it's complementary to the perspective that we heard about previously, in that I will not make reference to a Euclidean path integral or even the Ryutakinagi formula. But there is also some difference in detail with the story I'll describe and the story that we discussed previously. One of the points, the physical points I would like to emphasize is that the results I'm describing suggest that in a sense, if you make complicated enough measurements, then the information about the black hole is always available outside the black hole, even before the page time. And this has a quantitative implication. It suggests that the naive page curve that we draw is not necessarily the correct curve for the von Neumann entropy of the state on Scri+, as I will describe. Okay, let me say just a few words about the philosophy of this talk. The way I'm going to go about constructing my arguments is that I will observe and make some analysis of some interesting properties of the semi-classical theory of gravity. And then I would like to make some precise assumptions about the full ultraviolet theory. And the assumptions will be that the ultraviolet theory shares, in a sense that I will make precise, some specific low energy properties of the semi-classical theory. And then if we accept these assumptions, this will allow us to extrapolate the results that we have for holographic information and gravity to the full UV theory. Of course, I want to clarify that and just the obvious point that there is no claim in this talk that semi-classical gravity is a complete theory by itself. But the claim is that the semi-classical theory does hold important lessons about how quantum information is stored holographically in quantum gravity. And those are lessons that we can already learn about without looking at the full ultraviolet theory. So let me now go on to some of the more and try and describe these results a little more precisely and the arguments that go into them. So I'd like to consider four-dimensional asymptotically flat spacetimes. And this is the standard form of such a spacetime in Bondi gauge. So there's a leading metric, which is just Minkowski space, and then there are subleading corrections to the metric. There could be dynamical fields, other massless dynamical fields, and then we'll use the standard boundary conditions, standard fall-off conditions for these massless fields. I'm going to be specifically interested in the algebra of observables on parts of null infinity. So in particular, I would like to look at the algebra of observables between a cut u and u plus epsilon, where u is this null coordinate that parameterizes null infinity. And this algebra includes, of course, observables, which are components of the metric, such as what's called the Bondi news and the Bondi mass. But more importantly, it will also include all possible products and linear combinations of these observables, which is what we usually do. We have some elementary observables, and then we allow the observer to also observe combinations of these observables. There is a special algebra that will play an important role in my talk. And that algebra is what I'll call A minus infinity. That's the algebra that I've marked here near this little red region. And it's the algebra near u goes to minus infinity of the theory. Okay, let me just review a few well-known features about the Hilbert space. We've known and we've analyzed a lot in recent years that the vacuum of these theories in four-dimensional spacetimes is infinitely degenerate. In fact, the vacuum, the various vacua are labeled by their eigenvalues under what are called the supertranslation charges. And then if you tell me the eigenvalues under all the super translation charges, that fixes the vacuum. But then on top of each vacuum, we can of course build a Fock space, which is the standard out space that we discuss. And the way you build this Fock space is just by acting with the various dynamical fields in the theory on this vacuum, and that lets you build up a Fock space. And then the full Hilbert space of massless particles is what you get by taking the direct sum of all of these Fock spaces that are built in these different vacua. And all the statements that I make in this talk will be confined to the space of massless particles, which excludes massive excitations, although I think it should be possible to include them, but I'm not going to include them in this talk. Okay, so now I would like to describe the first result, and the first result is as follows. I'd like to claim that if you look at any two distinct states in this direct sum of infinite Fock spaces, which is the Hilbert space of massless particles, then any two distinct states in this Hilbert space can be distinguished just by observables in A minus infinity. And that's a precise version of the statement that the information is always available near the past boundary of future null infinity. Okay, so I'm not going to go through the proof in great detail, but I'll just try and sketch the various steps that lead to this kind of a result. The first step is a technical observation. It is the fact that if we assume that in the full theory, the Hamiltonian is positive, then that gives us a familiar property of the theory. And that familiar property is that if you look at one of these subspaces that's built on top of a particular soft vacuum, then you can get any state in this subspace by acting with an operator from A minus infinity on the vacuum on which this subspace is built. So this is like the familiar map that we have between states and operators in quantum field theory, and it will hold in this case as well, and you can prove it more formally if you're allowed to use the positivity of the full Hamiltonian. I'd just like to make a note of caution here, because sometimes this sounds like a confusing statement if you're not familiar with it, but this is an intermediate technical step, and in fact it does not even require dynamical gravity, and this step, I think this is a true and important statement, but it is not the main point of the argument that I would like to make. The main point of the argument, the main physical point, I think that's relevant for this result, is the fact that both the Hamiltonian and the supertranslation charges are elements of this algebra A minus infinity, because they can both be measured from the past boundary of future null infinity. Now, there is a physical implication of the statement, and the physical implication of the statement is as follows. Consider what happens if you were to measure a supertranslation charge in a given state psi. Then the usual rules of quantum mechanics tell you that one doesn't get a definite answer, but one could get an answer between S and S plus delta S with a probability that's proportional to the expectation value of some projector in the state psi. So these projectors, which project onto specific eigenvalues of these supertranslation charges, and also the projector onto the manifold of vacua, which I'll denote by P omega, which is what tells you the probability that if you were to measure the energy, you would get 0. These projectors are physically observables, and they are part of the algebra A minus infinity. In fact, if you were to make a measurement, this is what you would really observe. Okay. Now, there is a surprising consequence of this. And the surprising consequence of this is as follows. What this tells you is that if you had a set of identically prepared systems, and you were to use the standard measure and discard procedure that one uses in quantum mechanics, where you make a measurement and you discard a system if the measurement is not what you want, you can use this to select a specific soft vacuum from near the past boundary of future null infinity. And mathematically, that's the statement that this operator, which is bra S ket S, is also an element of this algebra A minus infinity. Now, I'd like to emphasize that this is the key physical point. The fact that one can select a specific vacuum using observables on the boundary of the space-time is a very unique feature of gravity. It is not true in any other theory. Even though there are non-gravitational gauge theories which have boundary charges, you can never use those boundary charges to select a specific state, which is something that one can do in gravity. Now, once you accept this, which I think is a result that can be established very clearly, then using other operators that live in A minus infinity, which have a given supertranslation charges, you can also construct these transition elements that take you, that look like ket S prime that cause transitions between these different vacua. And these are also elements of A minus infinity. And they're just obtained by taking these projectors and multiplying them with some operators that have supertranslation charges. Okay. Now, this is actually sufficient already to sketch how the argument for the result goes. And the argument for the result now goes as follows. Consider any operator that maps the space of massless particles back to itself. Of course, by the usual rules of quantum mechanics, you can expand this operator in a complete basis. In this complete basis, you have a sum over these different soft sectors, and then you have a sum over states in those given soft sectors. But now, by the first technical result I mentioned, you can generate all these excited states in a given soft sector by acting with an element of A minus infinity on the given soft vacuum. And then by the important property of gravity that I mentioned, which is that this operator in the middle is an element of A minus infinity, you see that on the third and last line, you just have a linear combination of a product of three operators that live in A minus infinity. And this is manifestly also in A minus infinity because the algebra is closed under linear combinations and products. And so this tells you that any operator from the space of massless particles back to itself can be approximated arbitrarily well by an operator near the pass boundary of future null infinity. Okay, now this was an argument in the semi-classical theory, but in fact you can convert this to an argument or a property of the full theory of quantum gravity if you make some very reasonable assumptions. And the reasonable assumptions that one needs to make are that the vacua in the full theory are still labeled by operators near the pass boundary of future null infinity, and operators that map the space of vacua back to itself are also contained in this algebra A minus infinity. Now, because these are only low energy properties, there are only properties of the vacuum of the theory or the space of vacua of the theory, it's reasonable to assume that the full ultraviolet theory will share these properties with the semi-classical theory. And if you assume this, then the previous argument that I made goes through, and you can argue that even in a full complete string theory, if you could construct one in four-dimensional asymptotically flat spacetimes, all information about massless particles would be available near I plus minus. Okay, if one makes stronger assumptions about the UV theory, it's possible to prove a slightly stronger result, which leads to the picture that I mentioned about how null infinity stores information slightly more intricately than ADS. And that is, as I said, the statement that all the information that's accessible through this algebra at A of U1, which is through an observer who makes observations near this cut at U1, can also be accessed by an observer at an earlier cut who makes observations at this cut U2. The way one goes about showing this argument is by noticing that in the semi-classical theory, it's possible to derive some commutators between the Bondi mass and other dynamical fields in the theory. I won't go into the details of these commutators, but in fact, these asymptotic commutators, and when they were first derived, can be derived in the full nonlinear theory of general relativity. And the reason that works, even though the theory of general relativity has such a complicated symplectic form, is because these specific commutators depend only on the weak field limit. So now if you assume that these commutators carry over to the full UV theory, this is not really a low energy assumption. It's an assumption about how certain commutators behave in a weak field limit. But if you were to make this assumption, then you would find that the Bondi mass acts like a Hamiltonian, but it acts like a Hamiltonian for operators at larger values of U and not like a Hamiltonian for operators at previous values of U. And therefore, you can use the Bondi mass to evolve information from the algebra at U2 to the algebra at U1 and get all observables there, but you cannot do the converse. And therefore, unlike ADS, you tend to lose information as you move up on future null infinity. Now, this is just a recap of the results I described and the assumptions that I needed to make. As I said, if you make two very reasonable assumptions about the vacua of the theory and the low energy properties of the theory, which are that the vacua are identifiable by charges near the pass boundary of null infinity, and that operators near this pass boundary can map one vacuum to any other vacuum, that leads you to the conclusion that all information about massless particles is available near the past boundary of future null infinity. If you make a stronger assumption about commutators from the semi-classical theory, which depend on the weak field limit carrying over to the full theory, that leads to the conclusion that information on any cut of scribe plus is also available on any earlier cut. This result 2 is stronger than result 1, but it also relies on stronger assumptions. Okay, so perhaps some of you are thinking at this point that this is some abstract argument about operator algebras, but what does it mean physically? So I think that this argument I described actually has a very concrete physical manifestation. It's related to the question that Andy asked at the end of the previous talk, and it's as follows. Consider that we have some astrophysicists, these are my little astrophysicists, who live near this past boundary of future null infinity. And then somebody sets off a bomb which creates a shock wave somewhere in the middle of the space-time. And then the shock wave propagates and is going to come and hit null infinity at a later time. The shock wave has a profile. I could also consider different fields and flavors, but for now it's just a gravitational shock wave that has a profile that's given by this function f. And the challenge for the astrophysicists is that working only near this cut at I plus minus, they need to figure out the profile of the shock wave. So they are not allowed to go up or wait for the shock wave to arrive at null infinity, but they need to figure out the shock wave just by making observations here. So it turns out that this is something that can be done concretely. And one way to do this is to measure the correlations of the Bondi mass with other dynamical fields near the past boundary of future null infinity. I want to emphasize that this is not just measuring the energy, not just measuring the Hamiltonian, but measuring the quantum correlations of the Hamiltonian with other dynamical fields. Because this is a two-point function, it's just a two-point function of simple operators, one can compute it reliably in perturbation theory, and one finds some answer, one finds this answer. Now, the important point about this answer is that if you know this answer, for u being in this region minus infinity to minus 1 over epsilon, which is in this little red region, you can completely reconstruct this profile function f. This is something that you can demonstrate more formally using analyticity arguments, but if you just look at this expression, you see that if you knew this function, this right-hand side for large u, you could do a series expansion in powers of x by u, and this series expansion would give you all the moments of this function f, which would be sufficient to reconstruct this function f. So this gives you, and one can generalize this protocol, this tells you in a very concrete physical sense how observers near the past boundary of null infinity can use these gravitational effects to obtain information about the bulk state. It's very important that such a trick cannot work without gravity. It doesn't work in local quantum field theories, and it also does not work in non-gravitational gauge theories. In a non-gravitational gauge theory, of course, you have the possibility of measuring the charge, which might be like the Hamiltonian, but non-gravitational gauge theories also contain exactly local gauge invariant operators, which just exactly commute with all elements of all operators that these astrophysicists can measure. So for instance, if you had a non-gravitational gauge theory and you didn't allow these astrophysicists to use gravitational effects, you could completely defeat them just by taking the vacuum and considering another state, which is a vacuum acted with e to the I f squared on 0, and there would be no way they could distinguish these two states without using gravity. It's also important that these effects I described, as I said, are not true in classical gravity, but they rely on measuring quantum correlations, and quantum correlations which rely also on gravitational effects. Okay, let me spend the last 5 minutes that I have in making contact with some of the previous talks, and I'm sure some of the subsequent talks. So one interesting result one can get by looking at these kinds of results about information is about the page curve. Now there is a common way to define the page curve, which is the way it's usually defined, or to define the von Neumann entropy of segments of null infinity, and that is done as follows. Consider some segment of null infinity that goes all the way from its past boundary to some finite cutoff at u, which is marked by this thick red segment. Then there is some algebra of observables on this thick red segment. And then one looks for that element of the algebra, which you call rho, which when traced with other elements of the algebra gives you the correct expectation value of those other elements of the algebra in that state. This is the way one usually defines the density matrix associated with a region in quantum field theories. But now there is something special that happens about gravitational theories and when this region is part of null infinity, and that is that by the result I just described, all elements of this bigger algebra, you can always find a representative that approximates them arbitrarily well already in A minus infinity. Therefore, you can always choose this density matrix rho of u, which is describing the state on this segment of null infinity, to just be some fixed sigma, which is an element of this algebra at minus infinity. And this tells you that if you define the von Neumann entropy, or if you were to define something more careful like the relative entropy, this is just independent of u and doesn't change as you go up. So in particular, it would suggest that the page curve for a system of this kind, which is the black hole that evaporates, and when you look at the von Neumann entropy of this segment, is just a constant. The reason this constant is not zero in this case is because I've ignored the effect of massive particles, but the fact that the naive page curve fails, it should not be a surprise, because the page curve is based on known to be incorrect assumptions about the factorization of the Hilbert space. If one goes back and looks at the derivation that Page had for the entropy of subsystems, that explicitly relies on the factorization of the Hilbert space. And in flat space, even the algebra on Scri plus does not factorize because there is a remnant of the constraints of gravity that remains as you go on Scri plus. Now I'd like to emphasize, and this is an important point, that it may be the case that perhaps an appropriate restriction of the algebra by throwing out some observables will mathematically yield the page curve. But the physically important point that I would like to emphasize is that the information is always available outside the black hole if you allow the person outside to make all possible measurements, even before the page time. You might also think that you've never seen this curve before, but actually you have. And it's a very familiar curve. And it's the curve that appears if one considers the entropy of small black holes forming and evaporating in ADS-CFT. So this is a cartoon of a small black hole that started from dust and collapsed to a black hole and then evaporated to Hawking radiation. And if one looks at the fine grain entropy of the bulk region near the boundary, which is this red region or this magenta region or this green region, this fine grain entropy is always zero, which is reflecting the fact that one can measure all operators by going close enough to the boundary and making arbitrarily complicated measurements. So I'd like to propose that the evaporation of black holes in flat space looks similar to the evaporation of small black holes in ADS. I want to emphasize that this is actually not inconsistent with the recent work on the derivation of the page curve. And that's because the recent work, which is very nice, but always considers gravity coupled to a non-gravitational bath. So schematically, the picture looks like you have a gravitational system and then you couple it to a bath. And by construction in this setup, the Hilbert space factorizes. And when the Hilbert space factorizes, it is guaranteed that both SBH and the entropy of the bath will follow a page curve. But the physical point I'd like to emphasize is that it's important to make a distinction between the question of black holes, and when you've coupled them to a region where there is just gravity just switches off beyond some point, and when you consider black holes which are coupled to a region where gravity is weak beyond some point. And the reason for this distinction is that we have learned, and I think the island story also re-emphasizes, that weak effects in gravity can often conspire to give radically different answers from local theories. And so I think we need to distinguish these two setups, and I think it is the case that in systems where gravity is non-dynamical beyond some region, the information emerges after the page time. But for more realistic black holes where gravity is dynamical throughout, I think the information is always outside.
Sorry,
Okay.
Suvrat, you have 1 minute.
I'm done. Yeah, I'm done. So let me just recap the results. So I argued the main result I wanted to present was that all information on future null infinity is actually present near its past boundary. And I think this is a precise version of the claim that degrees of freedom on parts of a nice slice must be identified. I think this has a physical lesson, and it tells us that an outside observer with sufficiently complicated measurements can always determine the state of even a young black hole. This is not inconsistent with recent derivations of the page curve, but it does suggest that these derivations are inapplicable when gravity is everywhere dynamical. Okay, so I'm done. Thank you very much.
Great. Let's thank Suvrat for a very nice talk. And now we have 10 minutes for questions. Please raise your hand. Ed Whitten, please.
Sorry, I was muted. When you discussed the page curve, you considered the state to the past of a cut of null infinity. Suppose instead you consider the state to the future of that cut.
Yes. Then I think you might actually get the page curve. It depends on how much entanglement there is between the soft and the hard degrees of freedom. This is something, but I think you might get the page curve. But the physical interpretation of that, so its question is, what if instead of this state that I've drawn here, you were to consider the complement of this region? So you were to consider how much information is available from the future to this region. And then I think you would get a more interesting curve and you might get the page curve, but the physical interpretation of that is slightly different. The physical interpretation of that is when you start out here, you have all information. And as you go up, it's like you're going inside, inwards, inwards, inwards. And of course, as you go inwards, you tend to lose the information that's outside and therefore you get some curve. So, but I should emphasize that even this is a result that I think relies on how much entanglement there is between soft and hard degrees of freedom. And as I said, the main physical point I wanted to emphasize is that it is true that an observer here who makes measurements here can always determine the state of a young black hole. And I agree with you that there are other definitions you could make that might mathematically give you the page curve.
Okay, next, Raphael.
Hi, yeah, thanks for the talk. I just wanted to comment that Aaron Wall and my students Sven Chandrasekaran and Ilan Halpern showed a couple of years ago that the Bondi mass is actually not in the algebra of observables of a finite interval of Scri plus. That follows both generally from entropy bounds or statements such as the quantum null energy condition. And it can also be seen operationally from the fact that quantum fluctuations become uncontrolled when you limit the amount of retarded time for the measurement, but you take the radius at which it happens to infinity, which is the limit that you would need to end up with a finite interval. Physically, it's simply the statement that you could have superpositions, for example, of different Schwarzschild geometries, which would result in a non-zero entropy if you could actually measure the Bondi mass at zero energy, since you wouldn't have any gravitational radiation arriving in that interval. Or put a different way, you could communicate between distant observers at zero cost and energy by asserting that they can measure the Bondi mass in finite time at Scri plus.
So thank you. I just want to emphasize that, I mean, we can discuss this. I know we've discussed this in the past, but in fact, this point is not relevant to the central result that I want to describe. And the reason for that is that, you know, if you look at the Hamiltonian or the super translation charges, which played a central role in my description, those actually live from u equal to minus infinity to u equal to minus 1 over epsilon. So you have an infinite amount in some sense of retarded time to measure them, even though that's very close to the pass boundary of future null infinity. So as we described in our paper, in Appendix B of our paper, you could just, you know, there's a very physical procedure by means of which you could measure the Hamiltonian, which doesn't even run into the problems that you have discussed. I think it should also be possible to measure the Bondi mass, which is a question of measuring something up here. But for the central physical result I wanted to mention, which is the Hamiltonian, you actually already have an infinite amount of retarded time because you have all this infinite amount of time near the pass boundary. And so I think this obstruction doesn't arise.
Okay. Next, Andy Strominger.
Yeah, you talked a lot about the super translation charge and diagonalizing the super translation charge, but there's a whole infinite tower of more charges from the Virasoro symmetry, from the sub-subleading soft graviton symmetry, and so on, which one might expect to play an important role in this kind of analysis. Have you thought about them at all, or what?
Yeah. I think the important question is whether the vacua are labeled by those charges or not. So I think our current understanding is that the vacua are labeled by super translation charges. Now I should say that actually
I wouldn't agree with that. The vacuum can certainly have angular momentum, for example.
Yeah, let me just make a statement that I think you would agree with. What is really important for my result is that the vacua are labeled by charges that are defined near Scri plus minus. So provided the vacua are labeled by observables near the past boundary of future null infinity, the argument I made would go through. It doesn't actually rely on the fact that the vacua are labeled only by the super translation charges. So I think you would agree, if I'm not correct, if I'm not wrong, that you know, all these other charges are can always be defined near the past boundary of future null infinity. And if that is the case, then I think this argument would go through. It would require some more bells and whistles, but I think it would still go through.
But maybe also, that's what I understood, but maybe also the specific structure of them would be useful in understanding how the readout worked.
Yeah, I agree with that, yeah.
All right, next, Henry Maxfield.
Yeah, thanks for the talk. So I was wondering, you seem to be suggesting that this page curve result relies on the radiation being in a somewhere where gravity is completely decoupled and turned off. Whereas, so you can play games even in ADS, for example. You can put a boundary geometry, which is maybe a small sphere where you create a pure state black hole, and then some large sphere, and you just join them with some narrow neck that just allows the Hawking radiation to slowly leak out.
Yes.
It's just something to give you a clean separation between the black hole system and the radiation system. So that seems to be the more important thing. I was wondering if you could comment on that in relation to your.
No, I agree with that. In fact, when we discussed this first, I mean, many years ago, our proposal was that one should actually use the so-called plasma ball that Shiraz Minwala and Ofer Aharoni and Toby Wiseman discussed, which is what's called a localized, it's a localized black hole in a planar ADS-CFT correspondence. And that black hole is localized in some transverse directions in the boundary theory. And then there's a clean separation between that region of the boundary theory and its complement. And because the Hilbert space of the boundary theory factorizes, one should be able to derive a page curve for that as well. However, in the situation of a black hole in flat space, if you're surrounding it in all ways, then I think that's not what happens. And it's also not what happens if you just take a small black hole, which is not, you know, you don't have localization in transverse directions, but a small black hole is just living near the center of ADS. So I agree with you completely that you could there are situations just in a single CFT where you could get this. And I think the plasma ball is the cleanest system where you could see this.
I think we only have time for one more question. Okay, Daniel Harlow. Daniel Harlow. Okay, is he here? Okay, then Andreas Karch.
Thank you. Maybe I have a direct follow-up to what just was said last, since
Sorry.
It's this feature that once you couple to some external bears, we recently demonstrated that will always tell you that the graviton gets a mass. So my understanding is that maybe this feature that you're finding, that you islands when you have gravity that goes all the way out to infinity, and you say you get the regular page curve only when you one way or another couple to an external mass. Can this be related to the fact that you do get a graviton mass the moment you couple to an external mass, and you wouldn't get the graviton mass if you really have gravity living all the way to infinity? Is this, you think this is related? I guess that's what I'm asking.
Yeah, thank you. This was discussed earlier, but I'm really sorry. I don't have something very sharp to say about this question of whether the graviton develops a mass if you couple it to an external system. So I don't want to say something.
I think that's a fact. That's just a fact. If you couple if you couple to an external system, the stress tensor is no longer conserved and the graviton gets a mass. I think that's undisputable. That this has something to do.
No, I agree with that. I'm not disputing it. I'm just saying that I don't have something intelligent to say about the implications of that observation for the story.
Okay, thank you. So unfortunately, in view of time, we really have to move to the next speaker. So let's thank Suvrat again for the beautiful talk.